Primero, buenos días a todos y la introducción la voy a hacer un poquito en español, obviamente, aunque luego el idioma oficial durante el día será en inglés, la charla será en inglés, pero tendremos tiempo, lo intentar hacer despacio y tendremos tiempo después de discutir cualquier punto que queráis en los intermedios. Bueno, en primer lugar, agradecer a Rosa y a la asociación por el esfuerzo enorme de poner todo esto de manera conjunta. Creo que va a ser realmente un mini congreso, unas jornadas excelentes, donde va a haber calidad científica y va a haber también pues, muchísimo conocimiento clínico, psicológico y muchísimas experiencias incluso de padres y de asociaciones que son muy importantes para hacer algo conjunto y que sirva como un paso adelante en lo que ahora ya, como veremos a lo largo de todas las charlas, ha ido avanzando un montón, que es el conocimiento sobre los problemas que tienen estas personas, las personas con síndrome de Williams-Beuren. Quiero agradecer también a Pablo Lapuncina, al hospital y a las autoridades que han hecho la introducción por la invitación y por el honor también de estar aquí como el primer ponente. Y bueno, ahora que se ha hecho la presentación, también agradecer a todos los ponentes que han aceptado y muy especialmente a Lucy y a Giuseppe, que ambos son colaboradores míos desde hace tiempo. De hecho, Lucy y yo empezamos en paralelo cuando los dos éramos fellows hace ya, pues creo que eran 25 años, o va para 25 años, y ambos empezamos simultáneamente. Yo estaba en Estados Unidos, en Stanford, y ella estaba en Canadá, en Toronto, y empezamos a tener comunicación, trabajando en cosas a la vez, compitiendo y de alguna manera colaborando, y mantenemos la amistad y la colaboración. Giuseppe ha llegado a este campo desde una formación mucho más básica y mucho más potente, de manera más reciente, pero también lleva en el campo trabajando en mecanismos celulares de enfermedad durante muchísimo tiempo y ha hecho unas contribuciones muy importantes para el conocimiento básico, que es fundamental para las estrategias futuras para poder conseguir nuevos tratamientos o nuevas mejoras en la calidad de vida de estas personas. Y bueno, sin ya dilatarme más, I'm going to switch to the other language, so I'm going to talk specifically about an overview of at least, probably more, 55 years of knowledge and evolution of the investigation in different aspects of Williams-Beuren syndrome. So this is the history of the description of the syndrome. It was described in the early 50s by a pediatrician, Guido Fanconi, and he described children with a biochemical feature that was hypercalcemia, and along with the hypercalcemia, they have some different or differential dysmorphic or malformations, dysmorphic features. A few years later, the hypercalcemia was discovered in many more patients, mostly due to the provision of vitamin D at high dosage to prevent rickets in Europe. And it was discovered that many of the children with hypercalcemia after vitamin D treatment did not recover well and have additional problems, cardiac problems, and some neurobehavioral problems. And the syndrome was called, not Williams-Beuren syndrome, but idiopathic hypercalcemia of infancy. And it was in 62 and 63 when two cardiologists, one in New Zealand and the other one, Dr. Williams, and the other one in Germany, Dr. Beurer, described the specific features of the syndrome, what are some distinctive facial features, along with cardiovascular manifestation that were clear, and was a narrowing of the aorta just close to the heart. That's the supravalvular aortic stenosis that was present in most of the children, along with other features that are the neurobehavioral features that we are going to describe further in detail in the next slides. So, since the 60s, there was a lot of clinical investigation and there were many clues, working mostly on the endocrine abnormalities, the hypercalcemia and other problems that the children had. And there's a lot of research going on during these years, but the most relevant advance occurred in 25 years ago when families with a specific cardiac malformation and a chromosomal abnormality were defined, and the cloning of the breakpoint and the identification of the gene that was in the breakpoint of these chromosomal abnormalities found that there was a gene that was disrupted, elastin, causing the cardiovascular features in this family, and then all the individuals with Williams syndrome were found to have a deletion of these genes. The deletion was likely to be larger, and research based on the molecular knowledge started when before it was just research based on the clinical knowledge. So for the last 23 or 24 years, there has been a lot of advance, and not only on the molecular mechanism, but there has been a clear clinical and neurobehavioral phenotyping, and we are going to hear about that in the last two sessions, in the next two sessions. One is going to be about the cardiovascular problems, and the other one about the neurobehavioral problems, and the molecular mechanism that I'm going to focus a little bit more because it's the field in which we have been working more in detail. And along with this, we have been able to generate models to try to work in vitro with cells and also with animals, and those have been absolutely instrumental to be able to discover findings in the pathophysiology of the disease, and also to start, and I will describe a few, some therapeutical opportunities and therapeutical strategies. So, of course, you all know what are the features of individuals or children with Williams-Beuren syndrome. They look like each other because they have some facial features that are common to all of them: thin lips, a narrowing of the bifrontal space, usually the short nose with a tip that is a little bit bullous, and these facial features are common to all of them. They have some intellectual disability with a specific profile that I will describe a little bit more in detail afterwards, and they are hypersociable, and they don't have fear of strange. The most important medical problem is the cardiovascular phenotype that is usually, as I already said, narrowing of the vessels, and the vessels are narrowing mostly in the places of high blood pressure, is close to the heart, so they have supravalvular aortic stenosis, but they may also have pulmonic stenosis, although the arterial problem is extended and is present in all the arteries of the body. And they have also transient hypercalcemia that is not apparently any problem because it doesn't cause any complication. They may have additional problems, mostly related to the connective tissue, short stature, and some endocrine abnormalities as well. It's sporadic. It occurs in about 1 in 7,000 to 10,000 newborns, and once there is a person with Williams syndrome, if that person has children, it can be transmitted to 50% of the children in an autosomal dominant fashion. So interestingly, a few years later, quite a bit later, in 2005, and Lucy was crucial in that, it was described the reciprocal duplication syndrome. While Williams-Beuren syndrome is caused by a deletion, there is specifically the duplication, the gain of the same genetic material, causes a phenotype that is somehow the mirror phenotype of Williams-Beuren syndrome. They do have also some facial features, but are quite distinct from the features of Williams-Beuren syndrome. They have, this nose is a little bit big, and the bridge is high instead of flat. The fins are quite the lips are quite thin instead of big, and well, they, instead of having some language preservation, they have problems with language and with behavior, and a high proportion of children with the duplication syndrome are within the autistic spectrum syndrome. They don't have narrowing of the vessel, but dilatation of the aorta, and they have hypotonia. This is also sporadic. It thought to occur with a little bit less frequency, about 1 in 15,000, and in this case, there are more cases of vertical transmission, and it's also transmitted to 50% of the descendant. Both pictures are called syndromes because these are a group of symptoms that are basically always present in all of them, but there is a quite variable presentation, and it's multisystemic. There are many systems that are affected. The neurobehavioral profile, I'm going to focus now on Williams-Beuren syndrome. As I already said, there is always some sort of intellectual disability, but the CI the cognitive or the intellectual quotient, the IQ, the intellectual quotient is in the 50s, 55, the average, with a wide range. But the specific trait, as I already said, is the high sociability, with showing high empathy, and all these features change with aging. And they do have problems related to the emotion. 2/3 of them may have some sort of attention deficits and hyperactivity. A high proportion of them have anxiety, and some of the anxiety is manifested as phobia or general anxiety. Many of them may have restricted interest. Although this is a phenotype that is thought to be and is supposed to be the opposite of the autistic spectrum, there is a significant proportion of Williams-Beuren syndrome children who may show autistic features that could be as high as 10%. And with full autistic phenotype, at least 2% of them have full autistic phenotype. One of the most striking features is the difficulty with visual spatial skills. They cannot draw things in 2 or 3 dimensions. If you ask them to draw the D, they can draw in this way. And if you ask to draw this specific figure, that is the common test that is done, this is the way that they can usually draw this figure. They see the parts, but they don't see the whole. This is an ability, the integration of the visual skill, that can be trained, and it improves with time. It's much later than any other individual, but this is a older individual. He's 27-year-old, and you can see that now he tries to draw something that integrates parts, but the drawing is really, really bad. So the other thing that is affected but is slightly preserved is the language. They have some language delay, and they can communicate quite well, although they have lower comprehension than expected, and they usually use complex expression and set phrases, but generally they look quite loquacious. The communication skills are relatively preserved with respect to other abilities. So, as I already said, what has been advanced much faster in the last few years is the knowledge about what is the cause of Williams-Beuren syndrome, and it's the loss of genetic material. It's a deletion that happens because of a specific characteristic of the human genome in a specific region of the genome, that is the chromosome 7, in the band 11.23, that there are sequences that are repeated. Those are segmental duplications, and these segmental duplications precipitate that in some cases during the cellular division that generates the spermatozoid of the egg, you can delete the interval. Sometimes it's not typical, but in most cases this block mediates a deletion that is specifically of 1.8 megabase. That means 1,800,000 nucleotides are lost. But the most common, that is almost 90% of the cases, is a 1.5 megabase deletion that occurs in these 2 blocks of segmental duplications that they contain genes, these specific 3 genes, and I will go back to this mechanism a little bit later. So the issue is that in the great majority of patients, there is a common deletion, and what is also relevant as a basic mechanism is that there are specific hotspots during these blocks that trigger this non-allelic homologous recombination, and some of these hotspots are in meiosis, in the meiotic division, and a couple of hotspots are in the mitotic division. And the other thing that is relevant is that the information that is lost is for about 26 genes, could be 25 to 28 genes, and these genes are deleted in most cases, except for the atypical cases. We know that the mechanism is that, so the recurrence risk is pretty low, although there are some genomic variants in the population that confer a slightly higher risk. It's not clinically relevant, so the recurrent risk for any parents with a child with Williams syndrome is really low. what is high is the transmission risk for an individual with Williams syndrome that will transmit to 50% of their descendants if they have children. So the other thing that we have advanced once we have the knowledge, I will go, is through the generation of mouse models. I will show you later how these models have been generated, but all the genes in the Williams-Beuren syndrome interval are in the same order in another region of the mouse chromosome 5, so all they are together, although the segmental duplications that flank the human region are not present in mouse. So mouse don't generate that spontaneously, and we had to generate artificially the genetic lesion in mice. But using mice and using the individuals with atypical deletions, just assuming that missing more genes could give a different phenotype than missing less genes, using all this information for many years and with the contribution to many groups. So we have figured out which is the map of the features of Williams syndrome in relationship with the genes that are lost. So I am showing here all the genes that are lost, and just to show a little bit, it is quite known that elastin is responsible for the cardiovascular features, and I will enter a little bit in more detail later. There are some modifiers for this, could be NCF1. The main genes for the cognitive phenotype are those shown in green, and there are genes that are also responsible for the metabolic features. And the contribution is not simple. It's not that there is one gene, one feature. This is quite complex, and as shown by a work done by Lucia that she will discuss a little bit later, some of those genes contribute to the modification of part of the genome. So the epigenetic modification of part of the genome is responsible for the expression of many other genes, and through this epigenetic modification, the consequences are quite wide and a little bit complex. Anyway, clinical research has been very important during all these years, as our group, along with other groups, had been involved in the clinical follow-up of many patients. We have data for more than 600 patients, and we had been able to see more than 200 in our group, in our hospital, in different places, in different times. And we have established a common protocol with medical exam that is used for many doctors. We evaluate neurocognition in depth, and there are also biochemistry and imaging done in a few patients, and in all cases there is molecular characterization, and I will show you how clinical research can contribute to know better the natural history that Pablo Lacuncina will discuss later, but also to be able to define the genes that are responsible for the phenotype that could be the targets for therapies. And what had changed clearly during the years is that while the age diagnosis 15 years ago was the mean 5 to 6 years, with a wide range. There are many who were diagnosed when they were adults. Now, currently, the mean age diagnosis is 2 years, so 2 years and 2 months. So it's something that is a clear improvement, and it's probably getting even down the age. So the availability of early diagnosis, of course, will provide a better prognosis for most of the children with Williams syndrome. So, as I already said, what is something that is already practical of this knowledge, even if you don't have the miracle therapy, is that you know what are the complications, and if you have an early diagnosis, you can follow and prevent and anticipate medical complications. So the connective tissue problems that are mediated by elastin haploinsufficiency can appear at different times. The cardiovascular problems can be problems also in the bladder. They could have a bladder dysfunction and diverticula of the bladder. They may have also intestinal problems with degeneration of diverticula and chronic constipation. So all these things can be anticipated, treated in advance by diet or education, and somehow could lead to a better clinical management. Has been mentioned during the introduction. This is a multisystemic disorder with many other rare diseases, and as all association of patients with rare disorder, they demand a better and more coordinated medical service. And this is something that is, of course, is a requirement that society should provide. Attending so many medical specialists and so many times per year is leading to an excessive load for families, difficult clinical coordination, and poor integration. So, as it was mentioned before, there is a program for rare diseases in Spain, and what is even better, the generation of European reference network for rare diseases, and the participation in those networks is going to be a very good contribution, ideally generating really multidisciplinary clinics specific in different geographic locations, and the availability of follow-up of many patients and obtaining all this clinical information for better research and better knowledge of the longitudinal and the natural life of this patient. I'm going to talk briefly about mouse models. The genes are in the interval, so we have generated mice with the deletion of the entire interval, mice with single gene knockouts, mice with partial deletions, with half of the genes, the other half of the genes. And as we will discuss later, there are some cellular models that are really also a great tool for research. One of them, initial works done by Giuseppe, was the generation of these neuronal cells, and it was published in Nature Genetics 2 years ago. And after that, there are some other publications with additional neurons derived from patients. So by reprogramming, you can study the neurons of this patient, and you can specifically look for the mechanism in the neurons, what is going wrong in those cells, and then figure out ideas to how to treat those problems. I'm going back to the comparative clinical studies. So also having mice and humans allow you to do additional clinical research. So this is a study done initially in patients. So we are studying patients for just biochemical parameters, and along with that, we have the mice that we can test also to make sure they have exactly the same problem, and then we can try to figure out better what is the mechanism in the mice. So those are the parameters. Some of them were already known, that they may have some problems with the thyroid gland, but also the other with lipids and with other biochemistry was not known. So just to make a long story short, we have found that, well, about 30% of patients have clinical or subclinical hypothyroidism, what means just an elevation of a stimulating hormone that doesn't translate in most cases in any problem. So it's not clear if it should be treated. So only when the levels are very high it should be treated, or probably when the levels of TSH are high, lower than 10, should probably not be treated. They also have hypotriglyceridemia, and you can also know now by the study in parallel of the mouse what is the gene that is responsible for that, and is the MXLP1. And you can also have hyperbilirubinemia. That is something that is not relevant, but about 20% of those children and adults have a slight elevation of the bilirubin that, well, you can only notice a little bit by the color of the sclera of the eye. So the other thing that we have been doing, I already mentioned how to figure out the phenotype by just comparing patients with atypical deletions, that are a few, but there are many other modifiers of the phenotype. So what are the causes of the variability, and what are the possible modifiers of the penetrance? So we have studied mostly the possibility of variants to modify the deletion, and also the breakpoint mapping, exactly where the deletion occurred. So this is the slide that I showed you before, and just to show that out of the 3 genes that are in the specific breakpoint with recurrent hotspots, depending on where the breakpoint happens, so you have copies of all these 3 genes, mostly NCF1 and GTF2 RD2, that can be expressed or not expressed. And those 2 genes can be somehow modifiers of the specific phenotype. Going to the cardiovascular features.
Perdón, 5 minutos.
Going to the cardiovascular features, elastin is known to be responsible for the cardiovascular phenotype, and this is what you see when you have 100% elastin, and this is when you have 50% elastin. So that leads to a narrowing of the lumen of the vessel with thickness of the wall. And then by these correlations, we have seen that NADPH oxidase is deleted when one of the C unit is either deleted or not deleted. So when it is deleted, it protects against hypertension. So individuals with the deletions do not show hypertension. So if you go back to this, what is the mechanism of hypertension is thought to be mediated with secretion of angiotensin II that then triggers the production of NADPH oxidase, and that leads to arterial hypertension. So if blocking by genes, you have lower hypertension, blocking the same step but different medications, and Victoria will talk about that, are possible therapies for Williams-Beuren syndrome, and some of them had been already assayed. And also the quantity of elastin and the secretion of elastin will be discussed in another talk. There is a clinical trial trying to modify the amount of elastin that is produced by the cells. So we also phenotype mice for behavior, and well, I'm not going to define specifically what are the tests, but there are different tests that test anxiety, cognitive function, sociability, and also in mice you can specifically look at the brain and look at the synapses, look at the transmission and see what is going on and what are the things that are wrong. So yes, the phenotype of the mouse with a specific deletion that is identical to the patient's shows exactly or basically the same features, the same clinical features of individuals with Williams-Beuren syndrome. They have increased social interaction. They have some locomotor problems, which are seen with the rotor test, and they have increased anxiety that can be seen with different specific tests that are easy to do. And when you look at the spines, you can see that they have lower spines and lower density, and the morphology of the spine is different. And this is mostly to the lack of one gene, because the deletion of GTF2I gives almost the same phenotype as the complete deletion. So we have shown the relevance of GTF2I in the neurocognitive phenotype, but we have also shown that we have the complete deletion that should be the model to attempt any rescue. And what we have done is to try to rescue the phenotype by injecting GTF2I in the brain of these mice and inserting that in a lentiviral vector. So this is done, is a sort of gene therapy done in situ that can be done in mice, not in humans, obviously. And well, you see a significant improvement in the neurobehavioral phenotype with decreased sociability. And interestingly, you can see changes in the specific proteins that are known to be involved in the social phenotype, that is the BDNF factor. Although in just 1 month of treatment, we couldn't see any reversion of the phenotype that was in the dendritic anomalies. So GTF2I regulation is a good therapeutic target for the features of Williams syndrome. And more recently, there's further evidence of the importance of GTF2I in human studies. So variation in GTF2I are present in individuals with extraversion, and it also predicts the reactivity of amygdala in healthy adults. So yes, variation in the gene is relevant for anxiety and extraversion, and it is an additional study shows that probably one of the mediators of this function of GTF2I could be oxytocin. So this is the conclusion. And finally, just before going to the 2 last slides, we had been searching for other targets because the problem with this phenotype is the one that I mentioned initially. Having the deletion of the genes causes a phenotype, so it's a matter of dosage, but if you put double dosage, you have another phenotype that is not good. So if you want to treat one phenotype, you should have to be concerned about the amount of the thing that you put, because if you put too much, you can cause another phenotype that could be even worse in some. So we have found that GTF2I-RD2 could be a modulator of the IQ, of the intelligence quotient, and also of anxiety. Give us significant result depending on where the breakpoint is. So when you have a specific pattern of copies of GTF2I-RD2, you have a slightly higher IQ, just pointing out that GTF2I could be a good target. And the final slide before doing the summary is that why there are individuals with very high variable phenotype, and in cases why it's so severe. What are the reasons for this phenotype? Why, as I said, although usually they are hypersocial and they have a completely preserved language, almost 10% may be autistic and 2% are clearly autistic. So we have then studied 8 individuals with Williams-Beuren syndrome and autism spectrum disorder by exome to try to identify other variants. And well, this is what we have found, that in at least 6 of them, I'm not going to tell you the details, in at least 6 of them, we have found only one is de novo, the other ones are inherited, but are variants that had been previously described as associated with risk of autism, but are inherited from normal parents. Interestingly also, the deletion is in most of the cases on the paternal chromosome, but I guess that the main conclusion is that most likely, like in other syndromes, just carrying the deletion makes individuals with Williams-Beuren syndrome more susceptible to get just a more severe phenotype just by any other event, either genetic or even environmental. So they just have a higher susceptibility at other variants inherited from normal parents that would just be a change in personality, would not be a causative for a phenotype, could be in them causing a more severe phenotype. So in summary, there is great advance in the knowledge on Williams-Beuren syndrome since the description 55 years ago. It is known to be caused by a recurrent mutational mechanism, a common deletion, and that has possibilitated an early diagnosis and counseling. There are susceptibility to additional problems, and there are well-established clinical protocols. The susceptibility for ASD is likely due to second hits and the possibility that they are more vulnerable to be affected by other things, genetic and non-genetics. And the pathophysiology of the disorder is by not just one single gene, by additive effects of more than one gene. Elastin and GTF2I are most likely two of the main players, although the picture is a little bit more complex, and you will see that in the following talks. But just finding or knowing exactly what are the molecular bases and some of the modifiers, we will see that there are already some specific clinical trials targeted to try to improve the cardiovascular phenotype and also the neurocognitive phenotype on Williams-Beuren syndrome. And as I already said, GTF2I is the main target, and many groups are working on that. So I would like to end with acknowledging all the people during the many years who have been working in the lab, the current and the previous collaborators, and many collaborators throughout the world, including Lucy and Giuseppe and other collaborators. And thank you all for your attention.